Today I will talk about the machine learning and the logistic regression. And first of all, my name is Joshua. Forgot to mention it. And then we'll first review about the linear regression, which I talked about last semester, and then go on to a logistic regression. So let's do a little bit of review on the linear regression. So linear regression is all about predicting y when new x is given. And the equation is a y hat equal wx plus b. And this is loss function. For the loss function, we use an equation called square error function, and it is y minus y hat squared. And our goal is to minimize the value of the loss function. So we're trying to minimize the value of the squared error function. So how do we do it? So we use a gradient descent, and if the slope is positive, the subtraction minimizes because something minus positive trivially decreases the value, and if the slope is negative, subtraction increases. So by using gradient descent, we can minimize the value of the loss function and update the values for the better prediction. So how do we find the new values? So we use a partial derivative, and partial derivative is from the calculus. So if we call y minus y hat squared as a SE, as a acronym of a squared error function, partial derivative of SE with respect to w is approximately minus y hat x. And because the constant minus 2 is negligible, we can pretend by dividing by 2, and that's why I said minus y hat x. So when we update the value, w becomes w minus the partial derivative, so w plus y minus y hat x. So for b, pardon me?
Can I ask what w represents here in the partial derivative? What are you taking respect? What are you taking?
So w is the weight. So if I go to this line, y hat is wx plus b. So we're trying to find the value of the weight. So w is the weight. Did it answer your question or?
Yeah, the answer.
Okay, so w is the weight. So like wx plus b. And so what we're trying to do is, like when we are given an x value, we need to find a y hat value that is close to y. And that's why we're constantly updating the w and b values by using a gradient descent. For the b value, we take partial derivative of SC with respect to b. And if we do the partial derivative calculations and divide it by 2, it becomes minus y hat times 1. So if we subtract it, the new value b becomes b minus y times y minus y hat. And all these calculations we have done will be in our code. So this is a basic drawing of a linear regression. So if we have a neuron, we have x value, w value, b value, and the forward pass becomes our prediction value, y hat. And the back propagation is using the gradient descent and constantly updating the values of w and b. And the back propagation is by using a partial derivative and the gradient descent. So we can basically make this neuron in our code. So this is the code that we have made on last semester. So this is the class neuron. So I wrote it on your Google Colab. It's in Python. So if I review it briefly, we initialize the values w and v as 1. The forepass, as I mentioned, is y hat equal x times w plus b, which is the linear function that we have defined. And we have a backpropagation function, the fifth function, and at the fifth function is where we do a forepass and doing all the gradient descent for updating the values. So for x value is actually a matrix value, 442 by 1, y is 442 by 1 matrix. If we run it, the result actually becomes this. But to get this result, so this is actually diabetes data. So if we use a matplotlib and using a scattered graph, and the linear line, the linear function line is our prediction line. And we can see how our neuron made a very good prediction. Like all the scattered dots, our defined linear function closely resembles the patterns of the scattered dots. So let's actually go on to logistic regression. So what I'm gonna do is I'm gonna explain, and then we are actually gonna code. So this is gonna be our code. Before we do, I'm gonna explain what logistic regression is. So logistic regression is a binary classification, and because it is binary, it differs from the linear regression. So for this neuron, I'm having multiple W values and B because typically all the data sets we receive is in terms of a matrix. When we do the calculation through forepass, the value will be between negative infinity and infinity. So the z value is between negative infinity and infinity. So we define a new function, which is 1 over 1 plus e to the power of negative z. If we go through that function, we get the value between 0 and 1. We define it to be a. And from here, we do all the backpropagation process using a gradient descent. So if the a is greater than 0.5, where a is less than 0.5, we define it to be 0 or 1. So if I say, if this is a breast cancer data, if I get 1, that means the person with certain properties has a breast cancer. And so in the linear regression, the loss function was a squared error function. However, in the logistic regression, the loss function we use is a little bit different. So it's really same. We are taking the partial derivative. It's same as the linear regression. We take the derivative with respect to w, with respect to b. And I actually have done all the calculations, but if you want to do calculation, you can actually do the calculation. But it might take a while. But like, if you do all the calculation, and if we subtract it, we get the new value. W becomes W equal W plus y minus a times x. We have a subscript I because it is a matrix with multiple values. If we do with respect to b, we get a new value of b, which is b minus partial derivative, b plus y minus a times 1. And we're going to plug that into our code. And we say backpropagation because in order to get W value, we do partial derivative with respect to a, and then z, and then w. And this is a chain rule from the calculus. because of the chain rule property, you can picture the back propagation process because it is going from A to Z to W because of the chain rule. So we're actually gonna code what we have done. So I'm gonna open my Google Colab, and this is where we're gonna code. Google Colab. Just a second. I'm trying to open. So I'm gonna switch my live screen. Wait. Change windows. Google tab. Can everyone see my Google Colab?
I can.
Alright, nice. So if everyone got their Google Colab or any IDEs that runs the Python, let me know and I'm gonna start coding. So let me know if you all got your IDEs ready. So I assume everyone got your Google Colab or any IDEs. So I'm gonna start. So what we're gonna write is first we have to get the data sets from the sklearn. So from sklearn data sets import load breast cancer. And this is because we wanna get the load breast cancer function. Load breast cancer cancer.data.shape cancer.target.shape. If we run this code, you'll realize that the cancer data we have received is a matrix 569 by 30 to 569 by 1. And if you wrote this, let me know so I can continue.
So Josh, do you want to explain one more time what we actually printed out? I know we printed out the shape of the. So we're printing out right here the data, and then so pretty much, I guess you could say, are we printing out the shapes of the training data and the testing data, respectively, the target data, like the labeled data?
Yeah. So what we are printing is matrix shape values of x and y. So for the x, you see the cancer data. It is 569 by 30. So that is the data that's gonna be x. Do you remember y equal wx plus b?
Mm-hmm.
So when we plug that data, the matrix 569 by 30 data into the x value, and the 569 by 1 matrix is going to be the target, that's the y value. So we have to match. So the left one is the x value, the data shape, and the y value is the result that we have to get.
Okay.
So I assume everyone wrote the code, so I'm gonna continue. So if I do x equal cancer.data and and y equal cancer target, and if I do from sklearn model selection import train test split x train x test y train y test train test split xy stratify y test size so what we are doing here is we're trying to separate between the train data and the testing data. So with the training data, we're gonna train our neuron model. And with the test one, we're actually gonna test how and predict how good it is. That's why we're separating between the train and the testing one. And the test size I put 0.2, and that means we are having 20% out of the whole sample data. So the random state variable is just any number, so it is not an important parameter. The test size parameter is important, and it is because we are having 20% data set for the testing size and 80% for the training size. If we just use all the data sets as a training testing model, and if we loop multiple times, the neuron that we make will literally memorize the whole data set. So in order to get the good prediction result, we have to separate between the training set and the testing set. So x is the value, like it's similar to a function like y equal wx plus b. Y is the target that we want to have the result. X is the data. So through manipulation, we have to match with a y value. So if we print x train.shape, x test.shape, you'll see initially it was 569 by 30, and now it is 455 by 30 and 114 by 30. And if you do calculation, the testing size is 20% of the whole data sets. So we have separated between the training set and the testing set. So did everyone get to this part, or?
Yeah, Josh, I'm just gonna ask, can you try to explain a little more what the matrix, the 569 by 30 matrix, what that data really represents? Because I think it'll be better if you can kind of elaborate what we're actually working with rather than just looking the size of it.
Okay, so matrix, how should I say, so each sample data is within a matrix. So yeah, I should say like this. For 455 by 30 matrix, we have 455 samples, and each sample has 30 characteristics.
Okay.
So we have 455 samples with 30 characteristics. So, um, because we have 30 characteristics, do you remember y equal wx plus b?
Yep.
W is the weight. Because 455 samples has 30 characteristics, W is gonna be 1 by 30 matrix. So with each sample, with each characteristics, we're trying to manipulate so that we can find the correct W, best value for W and B.
Okay. And when we're splitting up,
So 455 is the sample number, and 30 is the number of characteristics.
Got it. All right, cool. And then we're splitting up our data into training and testing data.
Yeah, and it is important because the result after training, the true result of how good our prediction model is based on our testing model. Because if we do a lot of iteration, that will make our model to memorize our whole data. And that is why very important to have a separate new data sets that the machine never seen before. So we got the 20% out of the whole data sets. So 80% we're gonna train with, and 20% the whole new data set that our machine never saw. We're gonna predict how good it is. In the code that we're gonna write, it's gonna have a 85% prediction correctness.
Okay. Yeah. Thank you.
So so from here, we're gonna write an actual neuron. So support NumPy. NumPy is a very good library tool for the, especially for the matrix. So let's do class Logistic Neuron. Definition init. And this is where I initialize. So we're initializing WMB for as self x t impedance sum x self, and if you remember from my drawing of logistic neuron, Z is actually the result. I can show you later if anyone hopes to see it again. Z is the value after you're doing the forepass, so x times w plus b. And the value can range from negative infinity to infinity. Self b return z, and this is a forepass. And we're going to do back propagation. Self x w gradient x times r e gradient r times r. And ERR stands for the error, and the error is the real result, the y minus our prediction result. Return w gradient b gradient. And the reason why we're multiplying is because if you remember, it's from the partial derivative. If we do the partial derivative, it becomes x times error and 1 times error. And we have to subtract those two values. And because the z value, z, ranges from negative infinity to infinity, we need an activation function. And the activation function it was in my drawing. It's 1/1 plus e to the negative z power. So exponent negative z and return a. So that is our activation function, and we're gonna have a fit function. And fit function is actually a standard name for the machine learning. That's where it calls the four-pass and back propagation activation function. Self x y epochs. Epochs is a number of iteration. And we're so what I wrote here is we are creating. So W is gonna be 1/30 matrix, and the reason is X shape um um yeah, train shape. For the train it was 455 by 30. So the X shape of 1 is a 30s. That's why it's gonna be 1/30 matrix filled with ones. The self dot b is 0. So we are initializing the variables for I in range epochs. The zip function, what the zip function do is it takes out the values of the matrix one by one. That's the zip function. And we're almost done in our coding. So z is gonna have the value from our four pass, and a is gonna have the value from your activation function.
Josh, I just noticed in the forward pass definition, did you mean to return z up there instead of zip?
Oh yeah, thanks. Yeah, return z. Yeah, return z. Error. So error, we're actually comparing with the actual value with our prediction value. And we're gonna have our gradient as well. Self got back. So we are calling the back propagation function that we have defined. And we're subtracting it. And this is how we update the values. It was all from your partial derivative. And then our last function is to predict. So what this function is gonna do is x gonna be the value of the x test. Yes, x test. So what we're gonna do is our input parameter for the predict function is gonna be the x test matrix data. And it is gonna call the fit function, and then we're gonna predict how good it is. And it is gonna be 85% correctness. I mean the mean. So we're doing four pass. So four pass activation. So it is basically like if it's greater than 0.5, it'll be 1. So it is trying to compare with the y value. So if I run it, no error. So since we made our own neuron, we're gonna create our own neuron right now. So just take neuron.fit x train y train. And the what is important about the forepass is for the forepass it says numpy. We're calling the sum function of numpy, and the x is gonna be 1/30 matrix, and w is gonna be 1/30 matrix, and b is just a constant, so 1/1. What numpy does is it multiplies each element of the matrix and sums it all up, and the result is a scalar constant. So if I do fit function, yeah, so you'll get this kind of your display. So we have just trained our neuron, and you'll let me know if any of you need help or more time. Just let me know. And then later, we're going to predict how good our model is. Does anyone need help or more time, or should I continue? I assume everyone wrote the code. So now we're gonna predict how good our model is. It's actually pretty simple. So we're gonna use a function called mean from the numpy. So so we're trying to predict function is the predict function that we wrote on our neuron. So we're trying to find the mean when our prediction equals the y test result. So we are using our testing set. So if we run it at 82%, and that is actually pretty good because this is actually a very simple code, and this code is bringing us to 82% correctness. So that is pretty good for the small neuron for this. Does anyone have a question regarding the logistic regression or? So
I know I'm
everyone,
typing right now, but I think I just typed something wrong.
oh, you're still writing?
I think I just typed something wrong because I'm getting an error in the final. Let me see what code block was this.
Which part are you typing
You
in
go
error?
let me see 4pass. Did I type something wrong here?
4pass?
Equals 1 2 MP something self.b. Oh, I'm a fool. I just didn't put self.b. I put b instead. So it didn't reference the
Okay.
attribute of the object. That should be good. Yeah, I gotta. Oh, because I didn't. I keep forgetting that you have to run the code blocks, or you can just run them all. So I keep forgetting that. All right, I'm good.
All right, nice.
So Josh, I actually have another quick question. Sorry. So is this all for the coding portion of the model?
Wait, sorry, I wasn't able to hear you well.
Oh yeah, sorry. I just want to ask: is this all for the coding section of the model?
Yeah, that is it for the logistic regression. We built a neuron, and we made a prediction that brings 82% correctness. Yeah.
Do you want to try to like? I don't know. I feel like for me personally, like maybe like trying to like explain what's going on here because it is kind of. I know you're pretty well seasoned in machine learning, but maybe for someone who's like just getting started, maybe we can explain like I guess I don't know a little bit more what's going on here. I know it's a lot to ask for, but I mean like
Sure. Since we since we have like more time, like 20 minutes. Wait. We actually have two options. Do you want to build a linear regression, or do you want me to explain more? Which do you prefer? You could build a code of linear regression, or I could explain more by pulling out PowerPoint again on the logistic regression. Which one do you prefer?
I mean I'll build a linear regression model. I think yeah that's fine. That sounds fine. I was just kind of wondering like I know applying this kind of linear regression model to machine learning it might be hard to picture visually at least how this is exactly.
So for the so you have your code on your computer. So if you if you see my drawing again, I think it'll make sense. Let me share my PowerPoint again because it gives you a visualized description of your code. So I'm gonna pull out my PowerPoint. So can you see my PowerPoint?
Yeah.
So what's happening is do you know the input value is W1 x1, W2
Yeah.
x2 and B? That's the input value, and that's the forepass. The forepass function is x times self dot W plus self dot B. We're doing the forepass here. So first we're doing the forepass, but like here there's only two x values and two W values. However, in our model, it's a matrix 1 by 30. So it's gonna be from W1 to W30. There's gonna be 30 of them. And we're gonna sum them all up, and that's gonna give us Z. That's why Z is equal to numpy dot sum x times W plus B. That's gonna be the Z value, and it's gonna be ranging from negative infinity to infinity.
So you can pretty much say that we have this, I guess, since we have a term or we have a size that's one dimensional, how about we call the weights a row vector, right? So a horizontal row vector. And we have our and we have our independent variables x, right? And we pretty much that's a column vector, and what we're doing is we're multiplying those vectors, right? That's pretty much what we're doing, element wise.
element-wise, it is one-dimensional vector. However, initially it is two-dimensional vector because it is matrix. Sort of like x and y plane. It is initially um two-dimensional matrix. However, in the fifth function, do you see the zip function within the for loop?
Yeah.
The zip function plows the element one by one, and that's why it becomes one-dimensional. Initially, it was two-dimensional, 455 by 30, but now because of the zip function, it becomes 1 by 30. We're pulling out 1 by 1.
Mm-hmm.
So initially it was 455 by 30, but because of zip function which pulls out 1 by 1, it is 1 by 30, and x is going to be the same. And we're going to multiply all of them, and we're going to add all of them, and it's going to bring us a single constant because the numpy is some function. And it is indicated inside the circle, like the plus sign. We're going to add all the w, x, and b. And that's going to give us z value.
Yeah.
And
it definitely makes sense.
Yeah.
I'm just trying to extrapolate a little bit more of a, I guess, visual. I can't really do a visual because I'm not drawing any. But,
So the data set itself, the x value, the data set is 455 samples. So 455 samples with 30 characteristics. And we're gonna match with 455 by 1 matrix, the testing, the y. So we have to match. So we have to find an equation that defines the y value.
Mhm.
So because it is binary classification, it has to be 0 or 1. If the z is from negative infinity to infinity, we cannot do the binary classification. That's why we need a activation function, which is 1 over 1 plus e to the negative z power. That activation function will make the z value to be between 0 and 1. And from that point, we are gonna do the back propagation. And because of the chain rule, we're first doing partial derivative with respect to a, and then z, and then w or b. That's why we're going back. That's why it's back propagation through the chain rule. And if we do a, updated value, a is either gonna be, if it's greater than 0.5, then we're setting as 1. If it's less than 0.5, then it's going to be 0. And that's our prediction. That's y hat. So if it's 1, that means he has breast cancer. If it's 0, that means he does not have a breast cancer. So, and we're going to compare with our actual values and then see how good it is. And when we compared it, it became the 82% mean correctness.
Alright, sounds good.
So, yeah, so, like, do you see, back propagation part, back propagation function, do you see x times air and 1 times air? We found all these equations from this slide. When we do all the partial derivative, this is how we're updating.
Mm-hmm. Yeah, that makes sense.
So this is the diagram for the whole code.
Yeah, that makes more sense now. Thanks, Josh.
Yeah, and the linear regression differs. It's different because it's not binary classification. So from here, there's no activation function. This is linear regression. We are predicting the y value. That's the linear regression. We are predicting the y, not 0 or 1. That's why it's a linear regression. But here, we are doing the 0 or 1 logistic regression. Also, if anyone wants to write a code for the linear regression, this is the sample code for the linear regression neuron. And this, if you picture it visually, it's gonna be this. It's simpler than logistic regression. This is gonna be the linear regression, and this is the code. If anyone wants to type it out, it is here. And if you want to type it out, make sure you import all the necessary libraries, like NumPy or any libraries. You have to import it before.
Yeah, if you just want to look that up so we could take it down, that'd be good.
Huh?
If you just want to leave it up so we can type it up or, write it down.
Okay.
I'll try writing it down. Anybody else have any other questions? Just, I know I've been firing at Josh a lot of the questions, but anybody else curious about or confused with anything? Do we all understand machine learning completely and seeing its completeness? Or I'm sure somebody.
I don't, and I don't know if I ever will.
I don't think anybody will. We can get closer, right? So ask questions.
Wait, Tony, was my description not simple or good enough?
No, no, it was good, Josh. I was just saying, I was just saying in general because it's a very it's very difficult topic.
Yeah.
It's a lot of the math can be like personally I'm just not very like matrices aren't I'm not very comfortable with matrices, so that can be a little difficult for me. But you did a good job, Josh.
Oh yeah, it was good. I just like to ask questions is all.
Hey, thanks guys.
No problem. Yeah, so I'm almost done typing up this fit method here for the linear regression. The linear regression model. So Josh, what is the goal with that? The linear regression model. It's trying to guess like a kind of like quote unquote line of best fit, right? Using possibly like the sum of squares method. I know that's a decent one. They use in statistics a lot.
Yeah, so linear regression model, when given x, it predicts y. So, for example, let's say you have a data set for the for the house. Like it'll have certain properties, and if I define it as x, I mean like it's gonna be like $3,000 or $4 million. It's gonna give certain numerical values ranging from negative infinity to infinity.
Mm-hmm.
Like I'm gonna ask like what's the price of the house, what's the price of the computer. By plugging in the properties, it's gonna give me some value, numerical value, like 4 million. But logistic regression is different because it's only gonna give me 0 or 1. The question I'm asking is different. The question I'm asking for linear regression is gonna be how much is gonna be the price, or how long it's gonna be. But logistic regression, it's gonna be yes or no question. Does she have a breast cancer? Is he gonna get healthy and get out of the hospital, or like yes or no, or like yeah. So or
for linear regression, maybe I could try to give an example myself. So maybe I have like 2 or 3 independent variables, right? Like when I'm trying to predict someone's level of like maybe activity, like health activity. So maybe one of the independent variables is like the number of hours they exercise, how many calories they eat, and how much time they spend in the house. Maybe I have those three independent variables, and I try to predict a y that says pretty much on a scale from, gives me a y value or a certain value of how healthy they are, right? That would kind of be something of like what you try to want to model with linear regression.
Yeah.
Am I right in that ballpark?
Yeah. And the like if you look at our code, we wrote a fair amount of code, but actually there are libraries and the you can actually write everything down within one single line. Like, you know how we have to build our own neuron, compile it, and then call our functions? There's actually many libraries, like a um
TensorFlow.
TensorFlow. In TensorFlow, the fifth function. Even if the person does not know all the calculation, like the fifth function, it does everything. I mean, there's so many libraries in TensorFlow. Like one single line of code will do much better than all our neuron code. And even if you, even if we don't know all the background process, the TensorFlow or other libraries can do the whole steps with one single line, like a fit function.
Interesting. Very interesting. Alright, well, I coded up that Neuron class while we were talking. So I don't have any data to use for it, so maybe I'll just keep it here.
Ah,
Find something to test it on.
so is everyone does anyone need help or more questions or? So if no one has a question or I think we can wrap it up. But like if anyone has like any question, you can always email me or send me a Discord chat. Yeah. So I think we can wrap it up now.
Cool.
Thanks for joining, guys.
Alright, thank you, Josh.
Yeah, thanks for hosting,
Thanks,
Josh.
guys. Thanks.
Have a good night, everybody.
And yeah, actually, I just want to give one final announcement before we all leave. So thanks for everybody for coming, and Josh, thank you for the workshop and all the work you put into it. I personally was not very familiar with logistic regression, so it's something good to go over for me, and I'm sure it helped other people too. And so coming up this week, we just have our side project development night tomorrow night, and that'll be at 8 p.m. On Friday. So if you have any side projects you want to work on, or if this workshop inspired you to start a machine learning project and you need some help with getting it started, you can come out tomorrow and ask some questions. Or if you have anything else you'd like to show or ask questions about, tomorrow is also a good space for that as well. Or if you just want to come and chill out and watch other people and see what they're working on, that's good too. But yeah, so that's all I have. And yeah, thank you everybody for coming, and I hope you all have a good night. All right, good night, everyone.
Bye, guys.